Hello everyone, I am Abhishek Kumar Chowdary, physics lecturer with Chaitanya. So we were discussing nuclear physics, and till now we have been through many interesting, important parts of nuclear physics. Radioactivity also, alpha, beta, gamma decay also, what protons exactly, how nucleus was been discovered and all. In the previous topic, what we discussed was the last topic. That discussion was about chain reaction. Chain reaction means in one fission there are some neutrons, they are again hitting the uranium, then again some neutrons. In that fission, in that chain reaction, we discussed two types, if you remember. First was uncontrolled, and for that I gave you example of atom bomb. For second, uncontrolled fission, atom bomb. But second, I told you, nuclear reactor, a controlled one, controlled chain reaction. Today is the topic of nuclear reactor, in which what will happen? Controlled chain reaction. Let's see. What is nuclear reactor? One more interesting thing, this is also known as atomic pile. Suppose in question somewhere in the place of nuclear reactor they are using atomic pile, you must know the same thing. Okay, nuclear reactor or atomic pile, what is it? It's a device in which nuclear fission can be carried out through sustained and controlled chain reaction. This is the important one, sustained and controlled chain reaction. So we have a device now called nuclear reactor, and we can actually control the chain reaction. How to control, how to make nuclear reactor, these are the topic of discussion for today's class. Okay, so in nuclear reactor, see, chain reaction is there. I'm not saying in nuclear reactor you can actually stop the chain reaction. Chain reaction is there, but in a sustained, in a controlled way. So this is really a, we can say, a positive chain reaction used for constructive purposes, can be used for constructive purposes. That's why we make it nuclear reactor. See, what fuel we are using? Uranium. Generally, if I would say uranium-233 is preferred, U-233. Product neutrons, obviously, interesting one. And neutrons, if they are again doing the fission reactions, then hitting, making unstable nuclear uranium, and then fission, then uncontrolled. So neutrons are obviously there, nuclear projectile. If you can slow it down, control it, then controlled chain reaction. You are not controlling it, then uncontrolled chain reaction. Radioisotopes and heat energy. All products are useful there. Or nuclear reactor, whatever product we are using, all are being used for some useful purposes. Okay, so this is the basic definition. You have now a device in which what you are doing, you are carrying sustained and controlled chain reaction using fuel uranium, and product you see the radioisotopes, the heat energy, and most important one, the neutrons is there. Fine. Now let's see a systematic diagram. First of all, before the discussion of this diagram is based on thermal neutron fission. You remember what was thermal neutron? Thermal neutrons are the neutrons whose speed is slowed down by the moderator. Speed slowed down, slowed neutrons called thermal neutrons. Okay, so this diagram is for this fission. See, in this diagram, what exactly is a nuclear reactor? Nuclear reactor is, you can say, a carbon core and surrounded by thin walls absorbing. Okay, so this is the core, this is the wall, you can see, control rods, steam turbine, heat exchange, water from condenser. This is all we are going to discuss what exactly is happening here. But obviously, first there will be a chain reaction and then you will control it. Okay, so there is chain reaction and then there is an arrangement to control it. So we will see one by one what all things are there, but in basic format what we can say, so it's a carbon core Core is basically, we can say, where the fuel, the nuclear fuel that we are using, like uranium we are using as a fuel. So that is being housed there. That is called core of the nuclear reactor. And to start with one by one point, what is nuclear reactor, what fuel, what moderator, what is the entire working purpose? To start with, we will start from nuclear fuel. See, nuclear fuel, what we are doing here, it's fabricated in the form of long conducting rods. Nuclear fuel, fabricated in the form of long conducting rods. Why it's long? Because the greater surface area is actually, you can say, helping the heat energy to pass through to the coolant. Heat energy, larger surface area, obviously the greater heat energy will pass through the coolant. So first nuclear fuel, they are fabricated in the form of thin long cylindrical rods and larger surface area, because greater amount of heat can be passed through the coolants. Okay. Next, moderator, we know. What are moderator? Moderators are generally used to slow down the neutrons. You know, in general, when uranium fission, if we will talk about, in that fission, the neutron which is in the product, one neutron is there making U-235 unstable to U-236. Then fission takes place. But in product also, you can see here product, in product also we have written neutrons. In product, the neutrons you are getting there, those neutrons you are getting there, those are having energy, you can say, of the order of like 25 mega electron volt. Can you actually think 25 mega electron volt ready for doing the another round of fission? Nuclear fuel fabricated in the form of long cylindrical rods. Okay, fine. The second one is moderator. Moderator we have discussed in chain reaction also. What are they? If you remember that neutron in that U-235 plus neutron, U-236, the fission reaction. Here I am talking about the product neutron. That product neutron in that fission reaction usually have the energy of, we can say, 2 mega electron volt. This is high energy. What moderator does there? We use moderator in nuclear reactors to slow down the speed of the product neutrons. And that moderator, there is a, we can say, elastic collision. Elastic collision there. Collision between what? Between that neutron and the nuclei of moderator. And due to that collision, the energy of that we can say neutron becomes around from 2 mega electron volt to 0.025 mega electron volt. So in very significant way, see, we are talking about controlled nuclear reactor. So you have to control the speed of neutron. And to control them, what we are using is called moderator. Generally, we use graphite, that is carbon, or water, heavy water. Paraffin wax is also used. So, what should be characteristic of moderator? Now, this is a question point. So, one point I want you all to note down. Moderator generally should have low atomic weight. One characteristic is this, low atomic weight. And the second one is, they should not absorb neutrons. Moderator should not, what should not? Absorb neutrons. So they are slowing it down, lesser atomic weight, but they should not absorb neutrons. So this is the key function of moderator. So after the nuclear fuel and the second we discussed was the moderator, the next one is the control rods. See what control rod we have just discussed in moderator, that moderator, they should not absorb neutrons. You know who is absorbing them? Control rods. See, materials that can absorb the neutrons. Cadmium we can use, boron we can use. These are using for absorbing the neutrons, and they can move in and move out. See, can move in or out of the holes of carbon blocks. What is this process of moving in and moving out? See, when the control rods that I said use boron or cadmium, if they are going in, what they are doing, they are absorbing more number of neutrons, and then the speed of reaction decreases. When they will come out, lesser number of neutrons will be absorbed, and then obviously the speed of reaction will increase. So it is controlled, isn't it? That's why the name is control rods. They control the reaction rate. They can increase, they can decrease by moving in, moving out. So what are control rods? Rods used for absorbing neutrons. They can increase, they can decrease the rate of reaction. Moderator must not absorb neutrons. Okay? After control rod, the next one is coolant. Everywhere we use a large amount of heat energy is being released there. Obviously you have to. In many other heat engines, in many other devices also we prefer to use this. In nuclear reactor, isn't it an obvious choice? A very high amount of heat is being released there. So, see what it does. It removes heat generated in the fuel element. Coolant, as the name suggests, it is being used to remove heat generated in the fuel elements. This is important for your question point of view. What kind of coolant you have to use should have high specific heat. Do you remember anything having high specific heat? Water you can use as a coolant. You know, water specific heat quite high. Should have high specific heat and high thermal conductivity also. Okay? High thermal conductivity. Suppose the question is asking you to compare which is the better coolant. So high specific heat, high thermal conductivity. The role is just simple, and the role is what? Remove heat generated in the fuel elements. Okay. After coolant, do remember this is important to tell you. Like in moderator, the atomic weight I said it should be less. Like in coolant, for specific heat and for thermal conductivity, there are conditions on this. Now next one, protective shield. See, what is this? In nuclear reactor, in the product, in the chain reaction, beta decay is there also. Gamma rays are also emitted. So these radiations there, it's not like you are getting neutron only and that's it. Gamma rays also there, beta could be there, beta decay could be there. So these radiations are there, very harmful for the persons they are working there. So to protect from these harmful radiations, what we use is called protective shield. So you can see this is used to absorb and reduce intensity of radiations. Obviously, when the shield will absorb, intensity will decrease. This is only to protect, as the name suggests, from the harmful radiations. What we are using here, we can use steel, lead, concrete, etc. So this is the function of, this is the work of protective shield, to protect from what? Harmful radiations. Okay, now we have just discussed the configuration, what we need for the configuration of construction of nuclear reactor. Now for a quick working, if you know what is coolant, what is protective shield, and what is control rods, there's individual purpose, uses, significance we have discussed. Now we will discuss a very quick working of nuclear reactor, get a very clear idea how nuclear reactor actually works. See, fuel rods, the first one, uranium fuel rods, they have been there placed in aluminum cylinder, okay, and some separation is there between, some distance, some gap is there, and in that gap graphite moderator is used. Okay, you know the function of moderator. First, there are uranium rods, fuel rods, obviously, nuclear fuel, and that is being placed inside a aluminum cylinder, fitted, and with some gap in between, obviously, and that gap, graphite moderators are there. Now, with suitable arrangement of that control rods, the raising and proper, so that they can properly move in and move out in carbon blocks. So after doing these all, what actually happens there? The uranium fuel rod you are using, so neutrons are produced. Neutrons are passing through what? Moderator. So the fast neutrons, those are passing through the moderator, their speed slows down. And slow speed neutrons are called, if you remember, thermal neutrons. So what we are getting here? We are getting here thermal neutrons. Okay, let me write it for you. Thermal neutrons. These thermal neutrons are obviously slow neutrons. And why these become slow neutrons? Because of the moderator. Now these slow neutrons, they are hitting the uranium. Okay, if you remember, U-235, 92 neutron, they are hitting it. What is being formed? U-236, 92. More unstable. Now what will happen? Fission, obviously. So the fission is there. Now the fission, the product neutron, is controlled by whom? Control rods, the boron cadmium rod. And they can move in, move out, they can control in a suitable manner what desired speed of, we can say, nuclear reaction we want. Accordingly, more number of neutrons they can be absorbed, or less number of neutrons can be absorbed by control rods. And along with that, what happens? Huge amount of heat energy is releasing there in fission reaction. Those heat energy are made to pass through proper coolants and then through water. What will form? For this, heat, coolant, that is water. What will form? Steam. And this steam is being used to rotate the turbine. So when turbine will rotate on the concept of electromagnetic induction or AC generator, on that basis suitable magnets are there and magnetic flux is changing there by rotating the turbine. So what we can produce there? Electric power. So this is how we use nuclear reactor for a constructive purpose of generating electric power. So can we say that electrical power can be generated by controlled chain reaction? Yes, we can. That is what nuclear reactor actually does. So students, here we are with a new reactor, breeder reactor, a very interesting one, breeder reactor. First we will see the introduction, then we will see what actually is happening here. Converts non-fissionable material U-238, let me tell you, U-238, this is called natural uranium. This is called, let me write this for you, this is, students, natural uranium. Okay. So breeder reactor, what it is doing, converts non-fissionable material into a fissionable material. Natural uranium is there and it is converting it into fissionable. It converts it into an isotope of plutonium, I would say. And you know what? Plutonium-239 has the fissionable property, fission, just similar to uranium-235. So plutonium-239 is being produced by what? natural uranium, do remember U-238 is a non-fissionable material. Natural uranium is a non-fissionable material. So before going to the reaction and all, just see what actually is happening here. In breeder reactor, what is breeder? It breeds, it produces more energy than it actually consumes. Non-fissionable to fissionable, it breeds more energy or produces than it actually consumes. That's called breeder. So there is a core, okay, and in that core there is a natural uranium, U-238. In breeder reactor there is a core, and in that core natural uranium is there, enriched by U-235. Natural uranium is there in the core, but that is enriched by U-235. Now, apart from that core, there is a shell also, and that shell is again natural uranium. It is of natural uranium U-238. Okay. Now, what will happen? See, if you remember, in the general fission of uranium-235, like we have taken example of U-235 fissioned into barium and krypton, there 3 neutrons was being formed. In some product 2 neutrons are being formed. So we have discussed that on the average we can take in the fission of U-235 2.5 neutrons on the average we can take. These 2.5 average number of neutrons, product neutrons, 1 neutron is the left for sustaining the chain reaction with 235. Complete reaction cannot be stopped and will not stop there. So 1 neutron is there for the controlled chain reaction, and the rest 1.5 is being consumed by, absorbed by the natural uranium. Let me repeat it again for you. See, if there is a U-238, okay, non-fissionable core, enriched with U-235. You know, if enrichment with U-235 will be large, there is no need of moderator even. Moderator is not needed if the enrichment of U-235 is high in the core where U-238 we are taking. Okay, let me repeat the process for you. In the fission of U-235, on the average 2.5 neutrons are released. So in the breeder reactor, the 1 neutron out of this 2.5 is therefore sustaining the chain reaction with U-235 only. And what is left? 1.5. That 1.5 is being absorbed by, or you can say it is hitting U-238. And by taking that neutrons, this U-238, the non-fissionable one, the non-fissionable, natural, this is being converted to one of the isotope of plutonium, whose fissionable property is similar to that of U-235. So what it actually is doing, it has consumed the lesser energy and producing the greater. Fission is there. Non-fissionable to fission. So breeds more amount of energy, breeds energy. That's called breeder reactor. So this is the actual overall working, and let's see this working in the form of reaction. See, this is U-238-92. What is this? This is natural uranium. 1 neutron is there. It is converting into U-239-92, and obviously energy is released there. Gamma rays released there. Now the next process, U-239-92, it is being converted in the nascent plutonium P-239-93. There is, you can see electron, and if electron beta, then this is what? Negative, with negative beta, anti-neutrino. Okay. Now this nascent plutonium is being converted into one of the isotope of plutonium 23994, again plus that beta and that antineutrino. So what was the actual reactant? 238, getting neutron. From where this neutron came? From the fission of U235. That's why the enrichment was there. So this is absorbing this, on the average we can say it is absorbing 1.5. For in this reaction we are showing absorption of 1, converting of 239 then to nascent plutonium and then to this plutonium 23994. This plutonium has a fissionable property similar to U235, that you must note it down. So what it actually did, it converted non-fissionable material to fissionable material. And why breeder? Breeder is from the word breed, because it produces the more energy than it consumes in the core. This is the breeder reactor, very interesting one. Okay, so nuclear reactor, breeder reactor, now the power reactor. Power reactor, nuclear reactor, used for generating electrical power. Used for generating electrical power. Okay. See, the same concept is there. In nuclear reactor, huge amount of heat energy is generated in the core. And such reactors have very elaborated cooling system. And that elaborated cooling system is using water. So obviously steam will be generated, which is used for rotating the turbine. So what will be generated? The electrical power. Same concept. Water, steam, turbine rotation, and what is happening? Electrical power is generating. So such reactors used for generating electrical power are called power reactor. In power reactor, what power is being generated? Power being generated is E into N by T. This is the formula for you. Obviously, what is P? P is the electrical power. This is the electrical power. E is the energy. Okay. What is the energy there then generally in a fission? This E, let me write it for you. This is in general 200 mega electron volt. We can easily convert this into joule also. By mega means like 10 raised to power 6 and electron volt 1.6 into 10 raised to power minus 19. So in joule also, if in watt power is required in the option, so you can convert this into joule also. And what is N by T? N by T is number of fission per second. At times it might be given in terms of dN by dt also. So this is, or you can say frequency of fission. So this is rate of fission, number of fission per second. In 1 second, how many fissions are there? Rate of fission is also there. Okay. So this is the power formula that is being generated by power reactor. But as we all know that the 100% efficiency is not possible, not in general possible anywhere. So if the percentage efficiency is given, like suppose if the efficiency is say X%, then power would be what? X by 100. And then the formula NE by T. So this is the power formula that we will be using in power reactor. And this is the energy value. At times energy value will not be given in the question. Then you have to memorize it as 200 mega electron volt. So today we have basically discussed the concept of reactor. Let me tell you, this concept is a kind of hidden concept. We know reactor is important, but we generally don't find it fascinating and do this, but conceptual questions might come on this. So important topic, all the topics were important, but conceptually what is the use of radioactivity, what is the use of fission that we use here in reactor. So this was the concept for today. Revise that, and in next class we will doing some numericals on this also, and then obviously then proton cycle is left and more interesting fusion concepts are left. So that we will doing. Till then, do revise nuclear physics, heading towards achieving 180 out of 180 in physics and 720 out of 720 in NEET. God bless you. Bye bye.